All right. So a couple of things. There were questions about the homework. I always set the homework so that it's you can turn it in up to 1 week late. I don't want to do much beyond that because I just don't want people accumulating massive piles of homework that I'll have to grade all in a rush at the end of the semester. But the homework will always be set so that you can turn it in a week late. You're mostly all graduate students. There are some exceptions. So I trust that you'll work independently and, that you'll think it's to your benefit to do the homework. All right. We are going to have to deal with guacamole for a little bit because we don't have any good alternative in place, but guacamole was working right before I left for class, and it's still working, so that's good. I wanted to kind of go through opening up Cadence and setting up an S-parameter simulation, just a few basics for those that haven't used Cadence before. So let's start with one of the matching networks from our homework. So I think we had to do starting at 6 gigahertz, we had to go from 10 to 50 ohms. And we had let's see, I remember I wrote this down.
Well,
yes, sir.
you want to show this?
I should do that. I should share my screen. Let's see, share. Here we go. All right. Let's look at the homework solution here. All right, so here is my tapped C match. We started at 10 ohms. We have a shunt cap, a series cap, and a shunt inductor. And I calculated this to be, let's see, 1.57 and 2 picofarads and 555 pico. Yeah, there we go. Okay. Yes. Oh, that's a different map. That's one of the other homework problems. Yeah, yeah. This is just one of the purely real ones. I was just saving one of the imaginary ones. We could do that also. Okay, so this is the network we're going to try and build in the simulation real quick. So let's, I move the control. All right, so have you all managed to get online and launch Cadence? I haven't checked to see if everybody's in. All right, we're going to open a terminal. And where is our title? RFIC. There we go. Setup Cadence RFIC. Okay. If you haven't used Linux before, I highly recommend using console as much as possible. And there are little shortcuts like hitting tab keys to, speed things up. My wife calls this nerd. We will open up Cadence using that source file. If everything goes well, it should have created a directory for you, and you should have access to all the libraries that you're going to need for this class. If that hasn't gone well for you, let me know soon. You'll be starting your project in earnest coming next week. We almost always start by opening up the library manager. And the first thing we're going to do is create a new library. And we're going to give it some name. And we're going to attach it to an existing technology library. And that library is going to be the CMOS 22 FDSOI. All right. And if that goes well, you should see the new library right here. It's important that you attach the library to a technology library. Otherwise, when you start to put schematics in and things like that, the display might not look normal. Let's go ahead and make a cell view. Let's call this test_SP. And we're going to start adding something. So Cadence is all driven generally by keyboard and mouse. So it's generally meant to be driven by one hand on the keyboard, one hand on the mouse. And they use bind keys to aid that. So to insert something into a schematic, you press I. You can reset the bind keys if you want. I'll show you how to do that at some point. And we're not going to do anything involving the technology library right now, so we'll just grab components from analog lib. So the library is analog lib. We're going to grab ports first. I'm going to give the ports a port number and nothing else for now. So I'll give port 1, 2, and I'm going to add grounds, G and D. Oops. All right. And then we needed to add components. What was our match again? It was starting from the 10 ohm side, cap. Okay. All right. So we'll add a cap. Another cap. And an inductor. Okay, I haven't bothered setting any of the values just yet. We'll do that in just a moment. I'm going to put some wires in. W is wire. And this port, yeah, from the 10 ohm was a cap. So I'm going to make one of these ports equal to 10 ohms. You can leave it at 50, and then when you read on this off of the Smith chart, it'll tell you that it's 10 ohms, or you can just make it 10 ohms. Okay. And this was 1.572 and 0.55. Okay, so when you want to edit a component, you can highlight it and press Q, and that will bring up the menu here. There's 1.57p. Or if you just highlight a component, for instance, you can go over to the property editor on the side and edit the, well, theoretically, you can do that. If you mess up, you undo. Must have had delete selected. What's going on here? You remember, huh? Oh yeah, dot. I never use the magnifier. My eyesight's perfect. All right, so our network's done. This is a pretty simple one. Before you can start any simulation in Cadence, the network has to be saved and checked, or checked and saved. There's a disk, floppy disk with a check mark on it to save it. And now we're going to launch ADE Explorer, which is going to be the simulation environment. Everything is built into the same window nowadays. So we're going to create a new view. We can just call it the same thing, and the view can be called test_SP. The view can be called Maestro. All right. Now, most of this stuff in the environment will already be set up for us. We don't need to change anything, but sometimes you will have to change model libraries, for instance. In our case, they'll be set up to work from the get-go. The one caveat is you are going to be working on RF and microwave components. So oftentimes you'll want to choose the millimeter wave library. In general, each of these things supersedes each other. So if you choose the millimeter wave library, it has all the other standard components plus additional millimeter wave components. In our case, this won't matter because we are not using any library components. We're going to add an analysis, SP. We're going to select our ports in the order port 1, port 2. And we're going to sweep across frequency. This was designed to be to work at 6 gigahertz, so 1 to 10 gigahertz should cover us. I like to do logarithmic sweeps, but you can do anything you like here. It's just going to change how it's displayed. We'll click OK, and we should be at this point for this relatively simple simulation, good to go. We can add some outputs in advance if we want to, but it's easier just to go ahead and run the simulation and add some plots afterwards. All right, that should have, yeah. All right, so once it's done, it's it'll open up an output log, and you'll see in this case it will have done S-parameter simulations at all the different frequencies that are listed here. And now we can go ahead and look at the results. We're going to go to results, plot outputs, or sorry, direct plot, main form. And to check the quality of the match, generally we want to look to see what the reflection coefficients are at the input and output. Remember, we're not looking exactly at the reflection coefficient, but we're going to look at the magnitude of S11. The magnitude of S22. This is a reciprocal network. So S11 and S22 are the same as long as it's matched. You can see that it's matched from about, we consider it to be a good match when S11 is less than minus 10 dB. So it's somewhere right around 5.1 gigahertz up to somewhere around 7.1 gigahertz, about 2 gigahertz on 6 gigahertz, which is roughly a quality factor of 3, which is what it was designed for. And we also generally care about the loss or the insertion loss. Remember, S21 is not equal to the insertion loss, but it's as long as it's matched, it's pretty close to the insertion loss. So I'll add that in dB also. We have ideal components here. So right at 6 gigahertz, you can see that the S21 is minus a couple of millidBs, so pretty close to ideal. Now, one other thing that we often like to do when we are looking at these circuits, looking at the magnitude is good. It tells us what the quality of the match is, more or less. But sometimes we also care about what the actual impedance is on either side, or if we're off in our match, we didn't quite achieve what we were looking for. If we look at a Smith chart, we can get some clues as to why we're off and what we can add in order to get the match to be where it needs to be. So we can add a new sub-window. I'm just going to add a rectangular window. It doesn't matter. When I put the Smith chart, it will switch it automatically. So we can look at S22, S11. And you can see if I hover my cursor right around the center, you can see right at 6 gigahertz, it's matched. Of course, the trajectory for S11 and S22 are different because the networks are different on either side of the circuit. Okay. Any questions about that?
So for the network, what if I switch the inductor and capacitor, like the position of the inductors? What they
we'd have to retune all the components, the match, and by the way, it might not be possible to for that network to work. I don't think it would.
Because the lecture, like capacitors recipe, is different configuration from the one that you showed.
So capped capacitor match is just a generic term where for a matching network where one of my impedances is connected to the center tap between two capacitors. So we can do it a couple of different ways. All right. Yes.
It's 1 parameter. How could you tell that the quality factor is 3 by just looking at the bandwidth?
Oh, so quality factor is equal to center frequency divided by bandwidth. We know that the center frequency here is about 6 gigahertz. And if I look at the match, we're looking at the minus 10 dB crossing point. So it goes from about 5.1 up to about 7.1, almost 2 gigahertz. So 6 divided by 2. Yeah. It will quality factor and the quality factor and bandwidth relationship is somewhat approximate here, but in other words, we're arbitrarily choosing the minus 10 dB point, but it should be a fairly close relationship. Yes.
Is there an intuitive reason for the thing was being bandwidth?
So, well, what we're looking at is a tuned circuit, right? And Q is really a measurement of how well the circuit is storing energy to how much power it's dissipating, right? It's only going to do that perfectly at one frequency, ideally losslessly at one frequency if there's no loss in the circuit. The more loss that I add into the circuit, the wider range of frequencies that it's going to have that energy storage function over, but the more the magnitude of the loss at the center frequency. Yeah. So yeah, hopefully that explains it. Okay. Hopefully you'll be able to get that far. By the way, I'm not sure. I haven't tried this out. ADS is also loaded, so we could do ADS simulations as well. You can set up S-parameter simulations in a similar fashion. Maybe I'll do a video on that at some point. Okay. Any questions on any of this? All right. How are you coming along with teams for your projects? Good. Okay. All right. So I apologize to folks that are in the internet or in the online domain. Apparently, the way that the class is set up, or at least the room is set up, when the class is over at 6:45, it will abruptly close everything. So I didn't, nothing crashed the other day. It just literally kicked me offline. So I'll try and be more mindful of that today. We were talking about noise figure. Let's go back to that. Well, noise factor. Noise factor and noise figure are related to one another. Noise factor is the linear version of noise figure. So noise figure is in dBs. Noise factor is in a linear term. Is in the linear domain. And of course, we know that because we found that the noise factor for a cascaded circuit like this one is equal to, for a two-stage circuit like the one shown right here, is equal to F1 plus F2 minus 1 over GA1. We're doing division here, which we can't do if we were in the log domain. So this is indeed noise factor. Okay, what we find if we have a cascade of more than, this is our cascade for 2 amplifiers. We can extend the cascade to more than 2 amplifiers or devices under test. And I say amps here, but theoretically it can just be any RF component. So more than 2 RF components we can cascade. And the cascading rules will look like so. The noise figure of the first stage, or noise factor of the first stage, is always going to be included directly proportionally. But any subsequent stage is going to be, the noise factor will be reduced by the gain that preceded it. So our second stage will have a noise factor F2 minus 1 divided by the gain of the first stage. If we were to add a third stage, the noise contribution to the total noise factor would be F3 minus 1 divided by GA1 times GA2. And we can keep going on and on like this. All right, so why is this important? Well, obviously we want to minimize the noise contribution that we have up front and put as much gain up front as possible. So when we look at a receiver, almost all receivers are going to start with a low noise amplifier as their first component. The low noise amplifier's main goal is to provide me a high amount of gain with a low noise figure. And nowadays that means gains on the order of 20 dBs, noise figures on the order of 1 dB, depending upon the frequency range that we're operating in. It's higher noise, lower gain if we're in the millimeter wave regime, but things will more or less be at least on that order of magnitude. Now, this cascading rule is also going to start to dictate, as I make a receiver chain, how do I want to organize my components in the receiver chain? I know I'm almost always going to put an amplifier up front if I can, but in a receiver, I'm also going to have mixers and filters and things like that. My mixers can have gain themselves, but they also usually have fairly high noise figures. I have passive noise figures that have no gain and moderate noise figures. So there are all kinds of choices that we're going to start to make. We're going to focus for the time being on the systematics, the reason that we make those choices before we start to go into the circuit detail, because I think it's a good idea to understand the receiver specs that are driving our choices. All right. So the primary spec that we're going to see in a receiver, there are a couple that we're going to care about, but maybe the first one that you'll ever see specified is the sensitivity. And the sensitivity is the minimum signal strength at which the signal can be received. And what we mean by received ultimately is that it has to be both detected and demodulated. All right. We can often detect the presence of a signal well below the power level at which we can determine what's inside of the signal. So if the signal is bearing information, we need a certain SNR in order to be able to demodulate it. All right, so the specification is going to tell us information about the radio system. And sensitivity is not necessarily, it's kind of an arbitrary number in the sense that a communication designer or a communication system designer is going to design a system, and they're going to design it to have a specific intent. So what range do they want the signal to be able to be received at? What's the transmitting power on the other end? All these kinds of things. The specification is just giving us some rules about how the radio system is supposed to be able to operate in its intended scenario. So the specification is going to tell us some things like what is the required sensitivity? And to do that, we're going to have to know some things like what is the signal bandwidth? What is the modulation that we're going to apply? How many bits are to be transmitted? Most modern systems organize their bits in payloads that they call packets. So how many bits are in a packet, for instance? And what we're really looking at when we talk about these receivers and sensitivity is we're ultimately going to start to look at signal to noise ratio. So for instance, we know that our signal, at least in the frequency domain, might look something like this. Now, the shape of the spectrum looks like this. We have no idea what's inside of the spectrum. It's just some, random, it'll change depending upon the modulation that's going through it, but more or less it'll have a shape that we can recognize. And of course, we're going to have some noise in the system. Now, the signal that we're looking at here, the information bearing portion of the spectrum is the bandwidth of the signal. And the power in the signal is, equal to the integrated signal PSD across the bandwidth divided by the bandwidth. And I should say PSD. What does PSD mean? Yeah, power spectral density. This just tells us an estimate of the power in any given unit of bandwidth. We normally will specify this per in something like a dBm per hertz. The power of the noise, we're also really worried about in our band of interest. It's equal to integral across the bandwidth of the noise density divided by the bandwidth. And we know that this is equal to, if this is just thermal noise, is equal to K times T times B. And our SNR is just equal to the signal power divided by the noise power. And for a given signal that we're interested in, there is a given SNR that we need. So this varies by the type of signal that we're looking at. What is the bandwidth of the signal? What is the how is the information encoded? And normally, at least the relationship between the signal to noise ratio and how the information is encoded, we find from these things called waterfall curves. We're going to look at one in just a moment. Okay. Now, ultimately, when we're making the receiver, what we really care about are a couple of things. Depending upon how the receiver is designed, we might care about the raw bit error rate. The bit error rate is exactly what it sounds like. The number of bits in error versus the total number of bits. Right. What's the worst bit error rate you can possibly have?
0.5.
If my bit error rate's 1, if I flip every bit, then yeah, the worst is 50%, 0.5. That means you have a completely random distribution of errors that you can't possibly fix. All right, we also often care about the packet error rate. And the reason is that they can do things like apply advanced error correction to the signal. And so we don't necessarily need to get every bit correct. We just need to get enough of the bits in a packet correct in order to be able to demodulate it. The packet error rate is equal to 1 minus the bit error rate to the nth power, where n is the total number of bits in a given packet. For Wi-Fi, we have a packet that's called a PSDU, which means physical service data unit. And for 802.11ax, AX is more or less Wi-Fi 6 standard. For Wi-Fi 6, we can assume that we have something like 52 million bits per packet. All right. And they specify in Wi-Fi the packet error rate, not the bit error rate. The packet error rate is specified as 0.1, 10%. So we can find the bit error rate from that. And the bit error rate is something like 2 times 10 to the minus 9. Not too bad. Every 500 million bits, you can get one wrong. This is actually not terrible. In wireline standards, they typically want something like 1 times 10 to the minus 13 or minus 14. They're also sending a lot more bits at a given time. Okay, so let's look at our at a waterfall curve. All right, so essentially, when we have a constellation, so I just drew a 16 QAM constellation up there. What we want to do is basically find out, what's the maximum possible signal to noise ratio where I can still detect any given signal. So, for instance, if this is my constellation, and I have a bit that's supposed to be, at this point, but because of noise, its uncertainty region is, much bigger. It can land anywhere in that red circle I've just drawn. I want to make sure that my system is spec'd such that I don't mistake anywhere in that red circle to be, trying to demodulate at, one of these particular bits. And so what this waterfall curve is doing is telling us ultimately, for different modulation standards that I look at, what is the SNR that I need to achieve in order to achieve a certain bit error rate. The more dense the constellation gets, the more information that I'm packing into the constellation, the higher SNR I need in order to be able to make a decision. You can imagine if all of a sudden in the same square, that 16 QAM square that I've drawn, I go from 4 bits per symbol to 6 bits per symbol. I have something called 64 QAM. I've packed a couple more bits per symbol in there into the same square. All of the points are a little bit closer together, and I need better SNR to be able to detect any given one of those points. So this waterfall curve tells us essentially how to figure this out. And for instance, this one doesn't actually quite go far enough because it's only going to 1e to the minus 9. So our curve for 2e to the minus 9 is somewhere right below here. But remember, we just said Wi-Fi needs 2e to the minus 9 bit error rate. Now, what modulation standard does 802.11ax use? Do any of you know what the maximum constellation is? Not for Wi-Fi 6, close though. 1024 QAM, or they call it 1K QAM, 10 bits per symbol in the constellation. So that is That is this one right here. Oh, and red, green is terrible color choice. I always forget. So 1024 QAM, that one right there. And so, what this is telling us is we need, we're looking at this curve and we need to find the point where it intersects with our required bit error rate. And that's going to tell us what our S and R is. But these waterfall curves are never, they're never plotted as S and R. They're plotted as EB over N0, which is the S and R per bit. So this will tell us what the EB to N0 is. All right, and you can see that here it's about somewhere close to 31 dB or 1K QAM. Now Wi-Fi 7 is even worse. Wi-Fi 7 is 4K QAM. So when you're trying to increase your information rate, you can either increase the number of bits you send per symbol, or you can increase your bandwidth, or you can do both. And they did. All right, so EB is the energy per bit. And you can imagine that you're integrating this across the whole constellation. Every bit in the constellation has a slightly different energy. And N0 is the noise power spectral density. Okay, so 1024 QAM, 1024 QAM. This means there are 1024 points in the constellation. How many bits can I send, or does each point represent? 10 bits. Log 1024 by log 2. All right, now the symbol rate is equal to 1 over the bandwidth. Anybody know how much their Wi-Fi 6 bandwidth was maximum? Not micro for sure. No, not quite that high. It's 160 megahertz. Almost everything in the Wi-Fi standard goes back to some multiple of 20 megahertz. They've added some additional features since then that go down to even 5 megahertz and below, but almost everything is a multiple of 20 megahertz. Oops, not 320. And this corresponds to a symbol rate of about 6.25 nanoseconds. Now, Wi-Fi 7 is 320 megahertz. So 320 megahertz, 4K QAM. So they've doubled the bandwidth, and they've increased the number of bits per symbol by from 10 to 12. So they've done something like 2.4 times more information at their max rate. All right, RB is the raw bit rate. All right, so here we're sending 10 bits at a rate of 6.25 nanoseconds. 10 bits every 6.25 nanoseconds. Now, this is the total. This is the raw bit rate means just the total number of bits that we're sending. It's not factoring in that they might not all be information bits. We might have encoding bits and bits for synchronization and pilots. But nonetheless, these are bits that we're actually transmitting. So we have a raw bit rate of about 1.6 gigabits per second. Pretty spectacular. Just over 100-meter wireless channel, you can send a gigabit per second. All right. So now to convert our SNR, our EB to N0 to an SNR, we multiply EB over N0 by the raw bit rate over the bandwidth. Normally, oftentimes this is given in EB units. So we have EB over N0 and dB plus 10 log 10 RB over W. So in our case, this equates to about 41 dBs. All right, so the SNR that we need to demodulate one of these Wi-Fi signals is around 41 dBs. Now, I'll point out that Wi-Fi and almost all communication standards, they have different what they call MCSs or modulation encoding schemes. So this is one of the higher data rates that you can send. Most Wi-Fi systems can vary the bandwidth, so they can go all the way down to 20 megahertz. In fact, some of them can go down to 5 megahertz. And they can also change the number of bits they send per symbol. So they can go anywhere from BPSK, which is 1 bit per symbol, all the way up to, in this case, 1K QAM, 10 bits per symbol. They determine how they're going to do that by doing a channel estimation, determining what the quality of the channel is. And from that, they determine what the maximum rate they can transmit. Yeah.
Here, when we're talking about bandwidth, are we talking about per channel bandwidth or the entire bandwidth?
This is the channel bandwidth. Yeah. So in this case, the 160 megahertz. Yeah. Our receiver is going to act like a filter and select just the channel that we're looking at. So, yeah.
Sure. If our contrast, I think you specify the noise power, and then you like multiply by 2 to get the noise power, something along those lines. You just a factor of 2 to get the noise power spectral density. Is that a concern for us?
Perhaps it was double sideband noise. I have to look to see what the specific case was. I think this is okay for what we're talking about, but there are cases where you might be looking at two-sided spectrum. I'm not sure. Okay, so our sensitivity is basically what we're doing is we're finding what the absolute power level is that we can detect the signal at. So we know that the noise power spectral density is KTB. We know that our receiver has some noise factor, and we know that we have some required signal to noise ratio in order to be able to detect the signal. So what you'll find, there are some things that almost all radio designers just commit to memory. So this term KT, which is the Boltzmann's constant times the temperature in Kelvin, at room temperature, which we're going to call 300 Kelvin, is equal to minus 174 dBm. All right. Another thing that we need to now remember is when we were talking about noise factor a moment ago, that's our linear version of noise of the noise degradation of a system. Noise figure is just the logarithmic version of that. So it's 10 log 10 of our noise factor. Okay, now where do we find these numbers? All right, so this is from the IEEE Standards Association. It is Wi-Fi is defined by the 802.11 standard that's made by IEEE. And we're going to look for sensitivity. And it'll tell us what the receiver minimum input sensitivity is. And let me move this box out of the way. All right, so what you see are that the standard itself has it has some different modulation schemes. So here you can go from BPSK, 1 bit per symbol, QPSK, 2 bits per symbol, 16 QAM, 4 bits per symbol, 64 QAM, 6 bits per symbol, 256, 8 bits per symbol, 1K QAM, 10 bits per symbol. They have different coding rates. So this is how many bits they have to add in coding in order to be able to demodulate the signal with whatever their specified requirements are. And then they have different bandwidths. So on the X axis on this table, they have 20 megahertz, 40 megahertz, 80 megahertz, and then 160 megahertz. And they give us what the minimum sensitivity is in each of these modes. And what you generally expect to see is as you move to a higher order QAM with a worse code rate, you need more SNR in order to be able to demodulate the signal. Also, of course, higher bandwidth, you'll need more SNR because the noise power spectral density will be higher for you. So, as you go across, you see BPSK, you start at a sensitivity of -82 dBm, and in the worst case, 160 megahertz bandwidth, you go to -73. And then, going down through the different MCSs or modulation encoding schemes, you get to a point where you see -43. The -43 is a sensitivity for our receiver when it's operating 1024 QAM, 164 or 160 megahertz. Now, every radio system has different specifications, and really the person that's designing the system has determined that they want this radio to be able to work down to -43 dBm in whatever scenario they're trying to push there. 160 megahertz, 802.11ax, that 160 megahertz 1024 QAM channel is not meant for me when I'm walking around talking. It's meant for me when I'm, standing in a relatively stationary position and I'm streaming high K, or 4K high definition video, to my laptop. As I start to walk around, the channel is going to get worse. I'm going to have fading going on, Doppler shifts, all kinds of stuff, and so they're necessarily going to have to relax the information rate they can push to me. Same thing happens in cellular networks. Of course, cellular networks are much more mobile than Wi-Fi networks are. Wi-Fi networks are intended for 100-meter range. Cellular networks are intended for kilometer range and more. Satellite nowadays. All right, so if we go back to our standard, we have a -43 dBm sensitivity. So if we just look to see what our what we need. The only real design constraint that we have in our system, I guess we have a couple of design constraints, but the biggest one that we as designers have control over is F, the noise factor. Yeah.
When you're calculating sensitivity, that noise figure is the
Is that noise figure today is the total system noise figure?
Yeah, this is the total system noise figure, right? So as an RFIC designer, we can't control KTB. We have an expected temperature range that we might be required to work over if we're selling a product. So for instance, normally when I'm selling a commercial grade product, I might need to have my system work from 0 to 85 degrees C. So KTB, I can't really control. That's Mother Nature and the HVAC systems that I'm working around. I can't control the SNR of the system. That's the communication system designer told me in order to operate with this spec, you need to do that. So the only thing as an RFIC designer I can control is noise factor. All right, so let's put everything together. So our sensitivity in dBs is equal to KT in dBs plus 10 log 10 of the bandwidth. So we're multiplying the noise spectral density, and I should say this is KT and dBm technically. There we go. And then the noise figure, and then the SNR in dBs. And substituting all the numbers in. I find that my noise figure needs to be less than 8.9 dBs. If it's any better than 8.9, that's great. That gives me some margin to meet the specification. If it's worse than that, it means I can't meet the specification. Now, I just do this at room temperature also. We should actually do this from the worst. What's the worst case scenario going to be? Probably 85 for a commercial. Most commercial products go to 85 C. So we should check this out over temperature and whatnot. Now, what I really should do is build a table that maps to the sensitivity table, and then I'll find out what my sensitivity needs to be. One of those other MCSs might actually be the worst case scenario. I believe that the 43 dB, minus 43 dB ends up being the worst case scenario for us. But generally we'll want to know what does our receiver need to do for all these different things. Because there are things that I can do to help design my system along, like when I can operate with a lower sensitivity, I can narrow the bandwidth of my system. I can maybe reduce the gain in my system. I can do things that save me power, right? Am I ever going to design a system exactly at 8.9 dB? No, I need margin because when I start making products in high volume, that causes me issues. And even more to the point, when I start making a product, if I can make my noise figure without having to spend a lot extra, if I can make my noise figure 3 dBs, then I just go and I advertise, on my chipset that my sensitivity is minus 48 dB. And I sell more product than my competitor. But anyhow, this at least gives us an idea of how to go from something in a standard to a specification. When we're going to make a receiver, we need to be better than this number. All right, any questions? All right. Let's start then for a few moments here. So the other major thing that we care about in a radio system is noise and linearity. Anybody can receive a signal if they have a perfectly linear channel with no noise in it. I can give that to most undergrads, and they can probably figure out some way to collect the signal and receive it. Where RFIC designers make their money is by being able to design systems that can receive signals in the face of strong nonlinearities with lots of noise. And I don't mean to insult undergraduates. I've got a few of them in here. You're pretty good, smarter than I was at the same age. All right, so for a MOS device, what is my relationship of current to voltage? Yeah, what is it?
Quadratic.
All right, 1/2 mu n Cox W over L VGS minus VTH squared times 1 minus lambda times VDS. All right, we're not going to write the square law for a MOSFET out too often anymore because, quite frankly, most MOS devices don't follow the square law any longer. At least none of the ones that you look at in this class will ever follow the square law. You're looking at 22 nanometer devices. Those are definitely not square law devices, but there is some exponent there, and it's nonlinear. The exponent is not 1. All right. But we can take some clues from this anyhow, and we still do use these things, these principles for a table-based design. So we care about the transconductance. Transconductance we define as dID by dVGS. So the ratio of the current that I get, a change in current I get for a change in control voltage, which is the gate to source voltage. This is equal to, or what we call it, GM, and it's equal to mu times Cox times W over L times VGS minus VTH. And we call this portion VGS minus VTH. Sometimes we call that the overdrive voltage. So how far past turning the device on and being in a linear range, being in the saturation region are we? We also denote from time to time GM as being equal to 2ID over VOV. This is a much more useful way to find GM because it's based upon ratios that we can quickly find from a simulation and not upon physical geometry of the device. And we have yet a third version, which is 2 times ID times mu times Cox times W over L. I should strike from the record the N up there. It doesn't matter whether we're using an NMOS or a PMOS. The equations are all the same. All right, so the thing to take from this, if I look at that equation, is that the current is non-linearly proportional to the voltage because of that square factor. And even if that square factor is something more like 1.5, it's still nonlinear. So we're still going to see distortion if we put a big signal into this system. Okay, so let us assume that we have a nonlinear transconductance. So in other words, our function of I with respect to maybe some DC voltage plus some small signal voltage, it can be expanded and it would take the form of C sub 0 plus C1 times V plus C2 times V squared plus C3 times V cubed. And we'll truncate it for the time being. We can keep expanding this, obviously, just a normal Taylor series expansion, but we'll just truncate it at third order for the time being. And let's assume that V is a two-tone signal. So V is a signal, has some amplitude, where we have one sine wave at cosine omega 1 of t, and we have another sine wave at cosine omega 2 t. And we'll further stipulate that omega 1 is close to omega 2. So these are two sine waves that are, right next to one another. So if we're looking at them in the frequency domain, we have two impulses that are adjacent to one another. All right, so what we're going to do is we're going to plug equation 2 into equation 1, oh, did I label? Oh yeah, we're going to plug equation 2 into equation 1, and we're going to do an expansion. And if we do that, I'm not going to take you through a derivation, because the only thing that's more boring than watching paint dry is watching a derivation, I believe. All right, so we have some, if we do that trigonometric expansion, we're going to get some DC terms. So these are terms that don't have any frequency relation. Whoops. We're going to have some terms at the fundamental frequency. We're going to have some second order intermodulation. IM is intermodulation. These are going to be beat frequencies. So we're going to have a cosine of omega 1 plus omega 2 of t. We're going to have a difference as well, cosine of omega 1 minus omega 2 of t. And then we're going to have some third order intermod. And these are going to be something like omega 1 plus 2 omega 2. Two omega 2 minus omega 1. Two omega 1 plus omega 2. And 2 omega 1 minus omega 2. All right, so we want a linear system where we put a signal into our system and we just get an amplified version of just the single tone. If our system was purely linear, if I put two tones into it, it wouldn't matter what the size of those tones were. I would just get two bigger tones at the output. But what do I get at the output here? All right, we're going to get a lot of harmonics. Because we're about to get cut off, I'm going to go ahead and stop here for today. But the key thing to take away is we have a nonlinear system. We put two tones into it. We get a bunch of stuff at the output, and some of those things are going to land in our signal band of interest, and we're going to have to deal with them because of that. So they will degrade the performance of our receiver, and we will have some specifications in our receiver that deal with that as well. the sensitivity is the minimum signal that we can receive. We'll also try and find the maximum amplitude of the signal that we can receive. And that will give us the dynamic range of our receiver. All right, so we'll stop there for the day. Homeworks, if you're a little bit behind, don't worry. You have until next Thursday to get it submitted. Projects, if you have your team already, please email me and I'll set up a group on Canvas so that you can, so that when you submit it, it will just link the submission together. And have you all found the paper that you want to do, or are you still working on that? Still working on it? Well, if you need some suggestions, see me. I put a few suggestions in there. Just make sure that you're looking at JSSC, TCAS 1, TCAS 2, MTT, quality journals in our field. All right, so see you next week.